Alright chemists, in this lesson we're going to look at how we use molarity as a unit of concentration when we talk about the stoichiometry in aqueous reactions. Molarity is defined as the moles of solute divided by the liters of solution. So that numerator refers to the solute. It's usually the minor component in a solution, and the liters is the entire solution. Now, many times we're not actually dealing with liters of stuff. We might be dealing with milliliters of stuff. So I'm going to rewrite this as an equivalent, which is if you have milliliters in the denominator, your numerator is a millimole. And we'll use those a lot. Millimoles are just 1,000th of a mole, and a milliliter is 1,000th of a liter. So a millimole over a milliliter is a molarity. There's an equation that goes with molarity that we'll use a lot. It's the dilution equation, and it's written as mv is equal to mv, specifically m1v1 is equal to m2v2. And all that really says, if you think about what you get when you multiply molarity times a volume, that is moles. And that just means moles equals moles, because if I have some solution molarity and some volume, and then I increase the volume, the molarity decreases, hence the word dilution equation. It's a very similar equation that's called the titration equation. It's MaVa is equal to MbVb. That just means acid and base. And if you remember our acid-base reactions from our previous lesson, they almost always occur in a 1-to-1 ratio. So if I have some amount of acid in molarity and volume, that's my moles of acid combined, well, that's how many moles of base it would require to react. So that's where that equation comes from. So what we're going to do today is use molarity and look at how we can get concentrations of ions and combine it with what we know about stoichiometry. First, let's just look at how we calculate molarity and practice this a little bit for some soluble compounds. So let's say I have 0.1 molar calcium nitrate and I want the concentration of every ion in solution. This is something that fully dissociates. So I get calcium ions, which if you want to write the concentration of something, you put a pair of square brackets around it. So this means concentration of whatever's inside the brackets, concentration of calcium ion. And I have 0.1 moles, that's 100 millimoles, divided by 100 milliliters. So all over 100 milliliters. No calculator needed, that's 1. If I check my seg figs, it looks like you need 3. So I have 1 molar calcium ion. And I know there's only 1 calcium in the formula, so my molarity, my moles of calcium, is how many moles of calcium nitrate I have. The nitrate has 2, so the nitrate concentration would be double this. So I'm just going to write 2.0 molar nitrate ion. Because when it dissociates, you'll get a 1-to-2 ratio of calcium and nitrate ions. So, once you hit pause and try the other two, what's the molarity of every ion in a 2.5 mole sample of sodium sulfate in 1.25 liter, and then this mass of ammonium chloride in 0.5 liter of solution? Okay, so for B, let's see how you did. My concentration of sodium ion is going to be, well, I have 2.5 moles of sodium sulfate. That means I actually have 5. That means I have 5 moles of sodium divided by a total of 1.25 liters. That's 4.0 molar sodium ion. And then how much sulfate do I have? Well, just look at the chemical formula. There's 2 sodiums for every 1 sulfate. So sulfate's going to be half of this. So for every 4 molar sodium, I'm going to have 2 molar sulfate. And then lastly, let's take a look at this sample of ammonium chloride. Here they give us a mass. So I actually need the molar mass of ammonium chloride. The molar mass of NH4 Cl is 53.45 grams per mole. I needed a periodic table to add up 1 nitrogen, 4 hydrogens, and 1 chlorine. And then to turn that into a molarity of each ion, it's ammonium, so bracket ammonium ion is equal to, well, in my head, I can actually tell 5.35 grams, 53.45 grams per mole, that's a tenth of a mole. So I have a tenth of a mole divided by half a liter. So that's 0.2 molar ammonium. And it's 1-to-1 ammonium chloride, so it's also 0.2 molar chloride. And I am intentionally toggling back and forth between using millimoles, milliliters, and moles and liters, really just to show you that they both work. It's sort of a personal preference. Which one do you want to convert if they're not already given in milli or the base unit? So now let's go one step further and look at what happens when we do a chemical reaction with volumes and molarities. This one says I have a 50 ml mixture of 0.1 molar lead nitrate, and I mix it with 50 ml of 0.1 molar potassium chloride. First, let's figure out the net ionic reaction that works. Well, remember from our first lesson in this unit, go find the spectator ions. Nitrate is a spectator, so I'm going to cross it out. Potassium is a spectator, so I'm going to cross it out. So I am left with chloride and lead 2. And my net ionic is just the sum of those ions, Pb2 plus chloride will make lead 2 chloride, PbCl2. That means I need 2 chlorides. And then it says, what's the concentration of every ion after the reaction occurs? So I need to use this information of volume and molarity for each one. And remember, volume times molarity is moles. So if I take my volume, 50, and my molarity, 0.1, that's a molarity times a milliliter. That combination will actually give you millimoles, and I can do that without a calculator. 50 times 0.1, that's 5 millimoles. So I have 5 millimoles of lead. I happen to have 50 milliliters of 0.1 molar chloride. I know that the molarity of the compound is the same as the molarity of the ion. I'm sort of in my head thinking about the skills we were using up here just because I'm picturing the formulas. Potassium chloride, 0.1 molar potassium chloride, that's 0.1 molar chloride. 0.1 molar lead nitrate, that's 0.1 molar lead. It would actually be twice as much nitrate if you remember and think about the formula of lead to nitrate. There's 2 nitrates. So this is actually 0.2 molar nitrate. I don't need that yet. That's a spectator, but we might need that when we come back to it. Anyway, back to this. I have 5 millimoles of chloride. So this is a limiting reactant problem. I take my millimoles divided by the coefficient for each one. Whoever's smaller is limiting. That's going to be the chloride. So I'm going to react all of the chloride, and I'm just going to keep track of it in these little columns that I'm building below each species. I'm just tracking how much chloride did I have, how much am I reacting, what's left over. I could do the same thing for lead. I started with 5. I'm not going to react all 5. For every 2 chlorides, I react 1 lead. So for every 5 chlorides, I'm going to react 2.5 of the lead. It's a 1-to-2 ratio. So I'm going to have 2.5 millimoles left over. So my chloride concentration is 0, because there's none left over. So chloride is 0, but I want the concentration of everything else that's still in solution, which is the lead ion, and then also the spectator ions. So let's go through each of those. How much lead ion do we have? Well, a molarity is a mole per liter, or, more simply in this example, a millimole per milliliter. And how many millimoles do we have? We just figured it out. We have 2.5 excess. So my numerator is 2.5. Now, what's my volume? How many milliliters do we have total? Let's assume volumes are additive So 50 plus 50 would give us 100 milliliters. So 2.5 divided by 100, still no calculator needed. I get 0.025 molar. But we're not done. There's 2 other ions that are actually swimming around. They've been there the whole time. It's the spectating potassium and the spectating nitrate ion. So how are we going to figure out how much of these we have? Well, they're in the same solution. So everything is in a 100 milliliter solution. But how many millimoles of each one do I have? What's my numerator for each case? Well, the potassium ion is a 1-to-1 ratio of chloride. So however much chloride we had in the beginning, that's how much potassium we had. And we figured out we had 5 millimoles of chloride. That means we have 5 millimoles of potassium. So my molarity of potassium is 0.05. And then what about the nitrate? Well, the formula for lead-2 nitrate is 2 nitrates for every 1 lead. And we initially had 5 millimoles of lead, so that means I'm actually going to have 10 millimoles of nitrate. These are spectator ions, so there's no reaction among them. So however many moles we had of them in the beginning, that's how many we have in the end. They're just along for the ride. So that means I have 0.1 molar of the nitrate. And there we go. There's our concentration of every ion left over at the end. There's our lead, our K+, and our nitrate. And we could even rank them. Chloride being the least abundant, it was the limiting reactant, so it's no surprise. Lead being the next least abundant, or the least abundant still in solution, it was the excess reactant. And then the 2 spectators are the most abundant because they were spectator ions. There's even more of the one that was twice as much of in the beginning. Okay, so what I'd like you to do is try the next 2. See if you could work out problems 16 and 17. These are both aqueous reactions. What's the reaction that happens? And then answer the question about the ion's specific concentration that they ask you for, and then check back and see how you did. Okay, for 16, it says we've got a volume of acetic acid, and we react it with a volume of some molarity of base. What's the molarity of the acetic acid? This is an acid-base reaction, HC2, H3O2, plus strong base, hydroxide, because of that spectating sodium, and that will simply make a water and an acetate ion. Whoops. There we go. C2, H3O2 minus. I'm going to use the trick we used before. Volume times molarity is moles, so I know how much hydroxide I have. I have 25 times 0.6 of the hydroxide. They're actually asking me, what's the molarity of the original acid? I know its volume, I know it's 45, but I don't know its molarity. This is actually the titration equation. I just have to put an equal sign in between. Because they react in a 1-to-1 ratio, my moles will equal my moles, or my millimoles equals my millimoles. So I just rearrange and solve, and you get 0.33 molar of the acetic acid, HC2, H3O2. Right next to it, this is not an acid-base reaction, this is a precipitation reaction. This is silver ion, cross out your spectators, nitrate, and in this case the H+ is actually a spectator for problem 17, although I just looked at it by finding the precipitate, silver and chloride. So I have silver ion plus chloride ion makes AgCl. I have 50 mils of 0.1 molar. That is, of 1.0 molar. So I have 50 millimoles of silver. And then I have 50 of 0.5 HCl. That's 25 millimoles of chloride. So the chloride is limiting, so I'm going to lose all of it. And I'm going to lose that amount of the silver, leaving me with 25 millimoles left over, and that's exactly what they want. What's the silver concentration at the end? So bracket Ag plus is the remaining 25 millimoles divided by the sum of the volumes. 50 plus 50 is 100, so I get 0.25 molar silver. So, hopefully you did okay on those. Let's just try one more before we end this lesson. Last one, what's the mass of sodium chloride that would completely react with this volume and molarity of silver nitrate to form AgCl? I always like to write the reaction so I can picture what reaction is happening. This is the same reaction as number 17, actually. Silver ion plus chloride ion makes AgCl. They give me a volume and a molarity of silver, 1.5 times 0.1. So that's actually 0.15 moles. Notice this is just moles, not millimoles, because this was liters, not milliliters. So I have 0.15 moles, and it's a 1-to-1 ratio. So I'm actually going to write some conversions right next to this. There is 1 mole of chloride for every 1 mole of silver ion. This is a little redundant, but I'll put it anyway. There's also 1 mole of sodium chloride per 1 mole of chloride, because there's 1 chloride in the formula. They want the mass, so I need the mass of NaCl. That's 58.5 grams per mole. So I just have to take 58.5 and multiply it by 0.15. That gives me 8.78 grams of NaCl. Mostly I did that just to remind you that even though we're using molarity quite a bit, you can always get back into grams just by using the molar mass of the compound. Okay, so that's how we use molarity for chemical reactions. The main thing to do is remember that multiplying molarity times volume is another way of expressing molar amounts, and concentrations are mole amounts divided by volumes, mole per liter or millimole per milliliter.